Hello and welcome to the Aspen video tutorials. This time we'll use reactors and heat exchangers in Aspen to model a boiler. So let's get to it. So this week's lab is reactors, boilers, and heat exchangers. We'll model the combustion chamber of a boiler to burn 100 tons per hour of natural gas in air with an oxygen molar excess of 10% in the feed. The assumptions for this model is that we have to state a reactor and reactor outlet pressure of 1.5 bar, set up the natural gas stream, then determine the molar flow rate of air, specify a duty of 0 watts to model an adiabatic reactor, and model a natural gas stream with these composition right here. Right, and there's some data collection after we've completed the Aspen model just to sum up our results. All right. So just starting off from last week's video, we have these components put in Aspen at the specification components tab here. We have methane, ethane, propane, butane, nitrogen, carbon dioxide, argon, and O2. But looking at the exercise here, since we're burning hydrocarbons and oxygen, we'll also need to add water as a component. So we'll just do that, water, and that's all good. And now that we have our components, we'll just go briefly to methods, and we'll still use Unifact as a method for calculating our properties. That's fairly easy. Now let's go to simulation. Right, so again, to start our flow sheet, we can put a block down, and for this session, we'll use a reactor. So we'll go to the reactors tab on the model palette. All right, and for this exercise, we're going to use a block called rstoich. So this is one of the easier reactor blocks to set up, and I'll show you in a little bit. So we'll just click on the rstoich and put that down. Right, and then the next thing we'll do is to connect the material to the rstoich block. Let's just expand that to make it clearer and add a material going in. So again, take note of where the red arrows are and take note of if these arrows are a feed or a product like that. So we'll also attach one for product. Right. So just taking note of what we have now, we have two streams, one going in and one going out. We'll assign stream 1 as our natural gas stream, stream 2 as our flue gas stream. Okay, and then for the natural gas, you can right click on the stream and select input, or you can go on the side panel to choose stream natural gas input. Right, so we'll just put ambient conditions for the stream, 21 degrees Celsius and 1 bar. And based on our exercise instructions, the mass flow rate is 100 tons per hour. So 100, then changing the unit to tons per hour. So metric tons an hour. Then we have our mole fraction. Just refer to the instruction sheet. So methane is 95%, 0.95. Ethane is 3.2%, 0.032. Propane, 0.002. Butane, 0.0008. nitrogen is 0.01, CO2 is 0.0052. That's it. Right. So a good check is to look at the total. If you expect the total to be 1, then a number 1 there would say you've entered your values correctly, right? And then, so that's already set up. You'll notice that flu here, it doesn't require any input because Aspen recognizes that it's an output stream. So what it will do is to calculate the properties and composition of your flue based on your setup of the incoming stream and the reactor, which is what's gonna come next. So if we click next, it'll lead us to the RStoich setup. So for this instance, you can specify operating conditions. Flash type could be temperature, pressure, duty, and vapor fraction. Yep. So for this instance, we want to set the pressure and the duty as specified on the instructions. The pressure we want, operating pressure is 1.5 bar, and the duty is 0. So it said 0 watts. So we can just change that quickly to 1. So our stoich is 1, which requires us to fill in 2 tabs, one specification and one is reactions. Right, and if you turn to page 2 of your instructions, exercise instructions, you can see these reactions. So there's 4 reactions for combustion of natural gas. And that's what we put in. So remember, we've defined the components in the properties component specification menu. So we can just select that here. Methane with oxygen. So I'm just pressing the first letters on the keyboard for quicker input, and water. Yep. And the coefficients just correspond to the coefficients on your balanced chemical reaction. So here it's 1 and 2. So you'll notice that for reactants, the coefficient is negative. That's because these components are being consumed. And conversely, for products, it will be positive. 1, 2. All right. And then here we have products generation, either molar extent or fractional conversion. For this exercise, we'll stick to fractional conversion and we'll just put 1, which is 100% conversion of component methane, because we want to model a complete combustion of the natural gas fuel. Then we click on next. Right, so that's all in there. Stoichiometry is well inputted there. So we'll just proceed with the other ones. To ethane, O2, CO2, water. And we have 2, 7, 4, 6. Then we have propane, oxygen, carbon dioxide, water. Propane's 1, 5, 3, 4. Then last one is methane, oxygen, carbon dioxide, water. And that's 2, 13, 8, and 10. And 100% conversion of butane as well. Right, so now that we have those 4, we can see that the blue checks are in. And we'll just go back to the flow sheet. So we now see natural gas coming in and flue gas going out. And Aspen would normally run this and tell you if there's anything wrong, so you can try to do that. But our chemical engineering knowledge, or even our chemistry knowledge, tells us that our reactions are with the natural gas components and oxygen. But our natural gas stream doesn't have oxygen, so Aspen probably will have a hard time calculating the products of these combustion reactions to the flue component. So we need to add another material stream. So still going to the feed port right there. So it's blue because it's already like the required number of streams has already been fulfilled, but we can add more than one stream. That's what we're going to do like now. Then we can edit the name and say air. Right. Okay, so we just need to specify air. So it's the same, 21 degrees, 1 bar. And let's just set, because we don't know how much air we need to put in. We just know it needs to be 10% excess. So what you can do is to calculate the air requirement using the stoichiometry of the mole fractions given for methane, ethane, propane, and butane. Use the stoichiometry given by the equations, calculate the moles of oxygen, and then calculate the amount of air needed. But at this point, let's just decide to put in the same amount of air as the natural gas. So that's 100 tons per hour. And we'll just have a look at what Aspen will calculate. So for air, we are given, let's look at that. So mass fraction of the components here. So just go mass frac. And we have nitrogen, which is 78.084%. Oxygen, which is 0.20947. Argon, 0.00936. Carbon dioxide, 0.00033. And water, which is 0. So again, the total is 1, so, and I expect that, so I think my data is all good. Right, so blue ticks all around. If I click next, then Aspen should ask me to run the simulation, which I will do now. So again, last time I pointed out that the control panel tells you if your simulation has run well or if there are errors or warnings. Yep, so this time we have a warning there, 1, and it's telling us that component O2 has 0 flow rate in the outlet stream. Fractional conversion has been modified by a factor of 0.544 times 10 to the minus 1. So it's saying that my oxygen in the reaction is the limiting reagent. It was not enough to react with the natural gas components, and so fractional conversions for all components have been modified from 1 to this very small factor. So when we look at the results here, yep, so there's that warning icon there. There's also another warning there. All right, and then we can look at the results of the reactor. So we have outlet temperature there, outlet pressure, heat due to 0 as we specified. And if we look at reactions tab, we have that extent. Okay. Another way to inspect the results of our reaction is to look at the stream results. So you can access that through the sidebar. Here, stream results. And that gives us a comparison of the streams entering and leaving the block. So we have air and natural gas going in and flue gas going out. Right, so we can compare temperature, pressure, and all of that. But what I wanted to point out are the flows. So we have mole flows and mass flows. We'll just look at mole flows at the moment. And for natural gas, we have these small flows for the natural gas components, for the 4 components that are combusting. And in the flue gas, we expect them to be 0 because they've been all combusted. But when we look at the flue stream, we still see lots of these natural gas components. So as expected, the combustion was not complete. So our specification of 100 tons per hour of air might not be enough for complete combustion. Right. So we just need to modify that. So prior to this lecture, I've prepared this table with the components of natural gas here, their mole fractions. So that represents, this number represents the number of moles per 100 moles of the natural gas. And then I've also put mole oxygen required per mole of fuel, which was derived from the equations, the chemical reactions here. So it's just that ratio of 2 divided by 1, 7 divided by 2, 5 divided by 1, and 13 divided by 2. So it's your simple chemistry, stoichiometry there. And then we can calculate the moles oxygen required for each 100 mole of fuel there. So it's just multiplying this column by this column. And we get a total of 202.72 moles of oxygen per 100 moles of fuel. Right, so it's more than twice. We need twice as much oxygen per mole of fuel. And then we want to have 10% excess. So we multiply this value by 10%, or 1 plus 10%, which leads us to this value, 222.99, or 2.23 moles oxygen per mole of natural gas. And then if we put in the spreadsheet the moles of natural gas from Aspen, so have a look here. So we have 5,935.94 kilomoles an hour. We'll just copy that to the spreadsheet. Yep, kilomoles natural gas per hour. All right, and then multiply that. So this times that times 1,000 to convert kilomoles to moles. And we have this moles O2 per hour. Right. And to convert that back to kilomoles O2 per hour, just divide that by 1,000. And then say kilograms O2 required. That, and just multiply that with the molecular weight of O2, which is 32. So we have kilograms O2 per hour. Right, and we wanted to have kilograms because our air is expressed in mass fractions, and thus we can back calculate air kilograms air required by dividing this value by the mass fraction of oxygen, 0.20947. We have kilograms air per hour, and then just convert that to tons air per hour by dividing that by 1,000. So we have 2,022 tons of air per hour. And that we can use for Aspen model. If we go back to air and put in 2,000, our model should run as we intended. So complete reaction for our 4 natural gas components and a 10% excess of air. So let's try that. All right, so for this instance, no warnings, no errors. And then let's just look at the stream results. So now, flue gas doesn't have any of the combustible components, methane, ethane, propane, and butane there. So that's good. And if we look at the excess oxygen here, so we put in 13,237 and we got 1,203.83 in the flue gas. So that's roughly 10% there, or probably 10%. So I think this model has been good. So we can now collect the data. We have to look at flue gas from reactor, which is this. We have to specify the flow rate in tons per hour, and we have that here as flows. But it's in kilograms per hour, so let me just change that to tons per hour. And we have 2122.12. So we can copy that to the table directly. Yep. Output conditions, we'll just look at temperature and pressure. So 1773 degrees Celsius and 1.5 bar. Molecular weight, you can see it here. Average molecular weight is 27.87. Specific heat, we'll get to that in a while. Let's just go density right now. And that's in kilograms per cubic meters. So gram per cc gets changed to kilogram per cubic meter, and that's 0.245693. And specific heat, if you remember how we did this, just go flue, stream analysis, point, right, and we want mass flow basis. Right, and just look at CPMX in kilograms per cubic, no, joules per kilogram Kelvin. So it's 1447.64. Okay. So just a quick reminder, if you have this data with all these decimal places, um, just lessen the decimal places, not just for aesthetics, but also to um, just recognize that the number of significant figures is not that many. You're not that sure about the accuracy of your data, so you can just reduce that. Just use 2 decimal places. All right, cool. And now we can also look at the composition of the exhaust from reactor, mole fraction, and mass fraction. And that's also in, we can look at the stream analysis or stream summary here, or we can just go Flue, right click, results. Right, so it just shows the results for one stream. We can do mole fractions. We have this, so we can directly copy that to our Excel. Yep, and then we just need to match it properly to whichever component it matches to. Right, and then you can do the same for mass fraction. Here, these. So nitrogen there, CO2 there, argon, O2, water. So you got two fractions here. One is mass fraction and one is small fraction. And then you can compare the differences here. They're quite similar. They're very similar for nitrogen, 0.74, 0.75 mass fraction. But for smaller things like oxygen or even carbon dioxide, the differences are bigger. So this allows us to be more careful when we're using composition specifications. So if you use small fraction, it might be a whole lot different than if you use mass fraction. So just take care when inputting data into Aspen or extracting data from Aspen that you know which fraction are you using. All right. So that's actually the first page done. Next is we need to determine the gross heating duty of the combustion chamber. Hint is to specify the pressure and temperature to be the same conditions as the inlet streams. So that's fairly straightforward. We go to setup, specifications, and we know our input streams is 1 bar. Instead of duty, we specify temperature, which is 21 degrees Celsius, and then click next. So Aspen will calculate the amount of heat that needs to be added or taken out of the reactor so we can maintain the temperature of 21 degrees Celsius and 1 bar and pressure of 1 bar going in and maintain it to the stream going out. Right, I think it's done. So if we look at the results of the reactor, yep, so outlet temperature is 21, outlet pressure is 1 bar, and the heat duty is this one, negative 3.5 times 10 to the 6, sorry, times 10 to the 8 cows per second, but we want it in megawatts, so let's just change that. And we get minus 1,468.96 megawatts. So it's almost 1.5 gigawatts of heat generated. Okay, and it's negative because it's saying that this heat needs to be removed from the reactor. So that's why it's negative. Okay, now we'll go to C, install a boiler or a heat exchanger in Aspen Plus to generate saturated steam at 202.83 degrees Celsius at the rate of 1,500 tons per hour. Ensure that the combustion chambers return to being adiabatic and 1.5 bar outlet pressure. Right, so we will do that. Setup. Revert that to duty of 0 watt and pressure of 1.5 bar. Okay, and then we need to use a heat exchanger. So under exchangers tab on the model palette, and we'll use one of these two-stream heat exchangers there. And then connect the flue. Just enlarge that. Connect the flue stream. Reconnect destination to the hot port. So we know that it's a hot fluid because it's 1,700 degrees Celsius. And that's the stream that needs cooling in the heat exchanger. So we need to connect it to the hot port. So this one's cold and this one's hot. So we'll connect it to that. Let's make a few more streams. Of course, we need the hot flue going out here. And then our cold streams going in. So, of course, this is modeled as a heat exchanger, but in reality, this can be the boiling section of the boiler. It's where your combustion gases or the combustion products transfer their heat from the combustion to the water being boiled. Right. So we know this one is water and this one will be steam. Right, so let's just specify this stream at ambient conditions, entering the heat exchanger or the boiler at ambient conditions 21 degrees Celsius and 1 bar. And as specified, you want 1,500 tons per hour, so that's a mass flow. You can put in 1,500 and then change units to tons per hour. And we know that this stream is 100% water, so we just put 1 there. So it doesn't matter here if it's a mass frac or a mole frac, because it's just 100% water. So that's all good. And then click next. And it leads us to specifying the heat exchanger, heat X. Here. So for this one, let's just do it quickly. For the model fidelity, we'll use shortcut and a countercurrent flow. Right? If we look at the specification, we can choose all these. So these are all different specifications with the different uses. So for example, hot stream outlet temperature, you specify that if you want to specify the amount of cooling you need for your hot stream. So it comes in at 1,700 degrees Celsius, but environmental regulations say that your flue gas should be released into the atmosphere at a certain level. So you set that. Or if you want maximum heat transfer, you can say hot-cold outlet temperature approach to be 1 Kelvin or 1 degree Celsius or 5 degrees Celsius. But for now, we need to generate saturated steam at 202.83 degrees Celsius. So that's going to be cold stream outlet temperature of 202.83. And in case that's not clear, our cold stream, as if you can remember, is water. And this water will be boiled in the heat exchanger by raising it to 202.83 degrees Celsius. That's the temperature of the saturated steam we want to generate. So blue ticks all around. That means we can expect the simulation to run. Yep, so no warnings and no errors. And that looks to be done. So we can, just by looking at the flow sheet, we can inspect what the stream results are by going into modify and just clicking these check boxes here. So we can add information about temperature, pressure, and I want to add mass flow rate to our spreadsheet. It looks the flow sheet looks a bit messier with these balloons here, but when you're just doing your simulation, it's easier to have these so you can just quickly inspect the results. All right, so as specified, we have that 202.83 degrees Celsius of steam. And then we see our flue gas has cooled from 1773 to 292. Okay, and now we can fill up the second table for flue gas exiting boiler, which is this. So again, results. And we can get the flow rate again for that tons per hour. And then our outlet conditions. So it's 292.353 and 1.5 bar. And molecular weight, it's the same. And then density, again in kilograms per cubic meter. And then specific heat again using point analysis. Yep, CPMX and the units we want. All right. Yeah, so we have these comparisons. So of course, the glaring difference is the outlet conditions. Flue gas exiting boiler is cooler. They have the same flow rate, molecular weight, the specific heat changes because of the changes in state, as well as the density. Right? And then the last question is to determine the heat duty or net heat duty of the heat exchanger. All right, and you can view that by clicking on your heat exchanger and getting to results. Okay, so you have here the summary of the conditions of the inlet and outlet streams, cold side and hot side there. And you also get this heat duty for the whole heat exchanger. And that will be important in sizing your heat exchanger. So just choose megawatts. as specified in the instructions, and it's 1163.8. So you have to get a boiler with a heat duty of 1163.8. Alright, so that's it for this exercise. Hope you learned something from this exercise, and just keep practicing your Aspen skills, and I'll see you next time.